Hello class. Today we are going to be talking about colligative properties. Now, before we talk about colligative properties, let me ask you a question. Why is it that we add salt to our roads in the winter? Why is that? Right? If it's minus 20, minus 10 in that range, we will add salt to our roads. Why do we do that? If it's a lot colder than that, we actually don't add salt. It's just sand. Why? Another question. Why is it that we add ethylene glycol to our cars? Why is that? It's also called antifreeze. It's in a name. What does it do? It stops the car from freezing up. But how does that actually work? So those are the questions we will be exploring today. So what is a colligative property? When we add a solute to some solvent, the very presence of those particles will change the physical properties of that solution. So when we add solute to solvent, no longer will the boiling point remain the same, no longer will the freezing point remain the same. Now, these properties are known as colligative properties, and the reason is because the number of particles influences the variation, right? It's the number of particles that determines how large this effect is, not the chemical properties of those things you're adding. The chemical properties are kind of still important, but it's the amount that really determines the impact on your physical properties. For example, if we look at sodium chloride and magnesium chloride, which of these would have a greater impact on the physical properties of water? What do you think? Well, when sodium chloride dissociates, how many ions does that sodium chloride dissociate into? It dissociates into two, right? Sodium and chloride. How about magnesium chloride? What does that dissociate into? It dissociates into 3 ions. So the magnesium chloride has a greater impact due to the fact that it just dissociates into more particles. It's the reason why we don't really use sodium chloride on our streets in the winter. When we use road de-icer salt, we don't use sodium chloride, we often use magnesium chloride or calcium chloride. Why? Because they dissociate into more ions and have a greater impact. So, why is it that your grandma used to add salt to the water when she was cooking pasta? Big myth. Most people think it's because it makes the water boil faster. It doesn't. It actually makes the water take longer to boil, but it does slightly decrease the amount of time that it takes to cook your pasta. And it seasons your food and makes it delicious, but that's besides the point. So how does it actually take longer? Why is it that it takes longer for your water to boil? Well, remember, what is boiling? What is boiling? A liquid will boil when the vapor pressure is equal to the atmospheric pressure. Right? When that vapor pressure is equal to that atmospheric pressure pushing on the solution can boil. When we add solute to that water vapor pressure lowers. Right? The vapor pressure of that solvent decreases. So in order to boil, we're going to have to heat it up hotter than normal in order for the vapor pressure to be equal to the atmospheric pressure pushing down. So by adding salt, we actually elevate the boiling point of that solution. So how does it do this? How does that boiling point get elevated? Why does the vapor pressure decrease? Well, first up, at the surface of our solution, where we have water particles leaving and coming back into solution, well, by having some of those spots at the surface occupied by solute, this decreases the ability of water to leave solution, and thus that vapor pressure pushing up against the atmospheric pressure isn't as strong. Another factor that comes into play is what happens once something dissolves. It will be solvated, right? Water molecules will surround that solute, and it becomes solvated. So in order for those now solvated water molecules to leave solution to become a gas, those solute-solvent bonds must be broken first before it can change phases into a gas. So energy needs to be expended there. And lastly, the heat energy added will increase the kinetic energy of the solvent and the solute. So the solute, you can think of it as kind of stealing some of that heat energy, because some of that heat energy is going towards increasing the kinetic energy of that solute, and not completely towards the solvent. So these three factors combined decrease the vapor pressure and thus increase the temperature required to boil your solution. Now, what about that second question? Why do we add ethylene glycol? Why do we add ethylene glycol to our cars? And why is it that we add salt to our roads? Why is that? Why is that? Well, we add salt to the roads to decrease the freezing point. Think about that, decreasing the freezing point. So it will melt at a much lower temperature. Now here's kind of the basic explanation. In order for something to freeze, an ordered structure with strong interactions must form. Right? In the case of water, right, we looked at that crystalline structure of water before. It forms a very ordered structure to become ice. Now the addition of solute makes it more challenging to form this ordered structure. It gets in the way, and therefore more removal of energy is required. So if it kind of gets in the way, we got to get it out of the way. We have to cool that solution down even colder than previous in order to get it to freeze. Now, this is where a student will always ask me, well, what if it's already like a big block of ice? Will adding salt actually still melt it? The answer is yes, for a much more complex reason. So here's the more complex answer. If this is a struggle for you, I highly recommend you. I'm going to link a video below. It's okay to be smart. And it talks about why ice is slippery. And it does a great job talking about what's happening at the surface layer of your ice. Highly recommend you check it out. It will help you understand what I'm going to talk about now, which is this quasi-liquid layer of water on the surface of ice. So at the surface of ice, there is less hydrogen bonding, right? We talked about this when we talked about evaporation. The further you go down, right, the more interactions there are. And those particles at the very surface, they do not have as many hydrogen bonds attaching them to that solid crystal. Thus, it takes less energy for them to leave and become a liquid. But as soon as these things become a liquid, they kind of just become a solid yet again. And this layer that forms on the surface of your ice is not quite a liquid, but it's also not quite a solid. We call it a quasi-liquid, and it is this quasi-liquid that allows salt to dissolve at the surface and have this freezing point depression effect. So adding salt will dissolve into the quasi-liquid, making it harder to re-enter solid phase by taking up space at the solid-liquid interface. Therefore, the freezing rate decreases, decreasing the freezing point. So really what's happening at the surface of your ice, under normal conditions, let's say it's minus 10 outside, you have some of that surface ice leaving, becoming a liquid, and then returning into the solid state. So as long as the rate of freezing is greater than or equal to the rate at which it is melting, then it will remain ice. But by adding salt, this actually interferes with the rate of freezing, right? It makes it harder for those water molecules to re-enter the solid phase, and thus the freezing point goes down. And the reason we do not use salt on, say it's a minus 30 day, is because adding salt can only depress the freezing point so much, to a point where it becomes impractical to do so beyond a certain temperature. So generally that minus 10 range is kind of like the sweet spot for salt de-icer. Okay. Now, all aqueous solutions display this freezing point depression. The more salt present, the greater the freezing point depression. And any foreign substance, like sugar, alcohol, etc., will cause freezing point depression. So, what does this mean in practical terms? Well, in practical terms, we use salt on roads, one I've already talked about. It melts ice very effectively at those kind of mild winter temperatures. Ethylene glycol is the main component of antifreeze, both in your car, and we use it as airplane de-icer. It's very effective at radically lowering the freezing point. And interestingly, many organisms have become specialists in surviving extremely cold temperatures. They actually produce things like large amounts of glycerol, which lowers the freezing point of their blood and allows it to still remain liquid at sub-zero temperatures. So that is all for today. We're going to be moving on to solubility curves, units of solubility, concentration, and kind of the math component of this unit. So everything up to this point has been theory. If you've been treading water and you're hating it, good news is the remainder is going to be math. Right on. Have a wonderful day, everyone.